what I want to talk about is the water cycle and its connection here to climate change. And as I was saying earlier, you know, here in Ohio, or really in the whole United States, we're a very wealthy country. I try to teach the students at Ohio State that, you know, we're rich. We can buy our way out of anything. Travel around the world, travel around to some of the other countries in the world, developing nations. They can't do that in comparison. So why do we care about global warming? A couple of degrees, I'm going to crank up the air conditioner. Bring it on, baby. You know, I'm tired of winter. It's a legitimate argument. Although it sounds silly, it is a legitimate point. So the legitimate point that I want to address in this, and there's a lot of ways you can look at that problem, whether you're talking about ecology or fisheries habitats or trees or whatever. I'm going to talk about water and its connection to climate change. And the upshot of it all is that as the Earth warms, the water cycle changes. The reason why I care so much about this global warming issue is how much water we have at any one place and time on the Earth is going to change. Our problem is we don't know by how much. It's because we don't have global measurements of water all around the Earth. We have little measurements here in the US, here, there. But go to the Congo. So in the middle of Africa is this big, huge river, second largest river in the world, and I can't really tell you how much water is flowing in there. I've got a good guess. It's about 2 to 2.5 times the size of the Mississippi. That's about it. That's about all we know. And yet it's the second largest river in the world. We don't know how much water is flowing in this river. So if I want to explain to you the global water cycle, and I can't even talk about the second largest river in the world in terms of a measurement, how am I supposed to really explain this global water cycle in a concrete way that you can walk away and say, hey, I know what's going to happen? This is why NASA and several space agency partners around the world are launching satellites over the next several years that will measure global precipitation, measure how much it's going to rain all around the Earth. It will measure, in a few more years, measure how much water is flowing in rivers and lakes around the world. We've got another satellite mission, so this will be the third one, that'll measure the moistness of the soil. So when it rains, you go out and you get your bare feet and you wander through your lawn. You're like, oh, the soil's all wet and it's gushy, right? Well, that's soil moisture, and it's because it rained. But if it's really dry and the soils are hard and you're like, man, I don't want to get tackled in football on that, that's a different thing, and we can measure that with satellites, and we can relate all these then to water availability. But how, you know, the classic thing you read in these various government documents that you've undoubtedly read, and where I pulled this slide from, you've read that it's going to, under global warming, it's going to rain more in the wet areas and be more dry in the dry areas. And when it does rain, it's going to rain with a greater intensity, but less frequently. Well, that's theoretical. We don't have measurements to really demonstrate that to the necessary accuracy that we'd like to be able to. So really, that's my point of it, and we could just sort of end there and have a discussion. But I always, so if you have questions, please just shut me off. All right, so here's a picture of the Earth that we're all very familiar with. But that's not really the picture I like. This is the picture I really like, because it takes the Earth and puts it on the edge. And so if you take, for scale, to get a feeling for this, when you're outside in your lawn and you're mowing the lawn, and you're driving your car and you look and you see the clouds up in the sky, and it looks like they're so far away and the atmosphere is really thick and huge and it's this big thing. In reality, it's very thin. So if there's scale here for this to understand how thin this atmosphere is take a classroom globe like you probably all have in your classrooms. It's about the size of a basketball. Put 5 sheets of paper, you know, so you've all got paper here. Here's a piece of paper here. Like, so take 5 of these, wrap it around the globe. That's the thickness of the atmosphere in comparison. And if you really want to be dramatic with your students, you just tear the paper and show them how easy it is to destroy the atmosphere because it is so thin. And this is the issue we deal with. We're very used to this view of the Earth because it's a beautiful view, and you get this notion that clouds and storms and hurricanes and everything are the size of continents. Yes, they are in their lateral dimension, but in their thickness, they're very thin, and therefore the atmosphere is easily perturbed. And these are the sort of scaling issues I like to bring forward to students. This is a simple box showing you where all the water is on the Earth. Now, these are guesses. These are pretty educated guesses, and we can round these numbers off by a little bit here and a little bit there, and it's really not going to make a difference. In other words, we don't have the measurements that concretely tell us these numbers, but they're pretty good overall. And no surprise, all the water in the Earth is in the oceans. And we know the depth of the oceans reasonably well. We know the sea level reasonably well. And so you can sort of get that number for the oceans pretty well. And then the fresh water is more of a guess. It's a good guess. But, you know, we don't drink the oceans. We drink the fresh water. And so that's the little tiny part we're most concerned about. A lot of it is frozen. And you'll hear, if you haven't already, you've heard about Antarctica and Greenland. It's all ice. So we're not going to get a hold of that water either. So the water we care about is this little tiny fraction, even though it's a full thingy drawn here, it's that much of that much. So it's a little bit of a little bit, which means it isn't much at all. And so you see the surface water part, that's the stuff here in Columbus. We're all from the Central Ohio area, right? Plus minus, everybody from around here? Okay, so the water you're drinking is coming from a couple of reservoirs. I happen to live on Alum Creek Reservoir. It's our backup. It's our reservoir in reserve in case we need it. The Hoover Reservoir out of Westerville is one of our primary drinking sources. In other words, we drink surface water. That's what we use. All right, so that's the little tiny fraction of the fraction of the fraction that we are most concerned about. And you see of that surface water, here's the part that's actually the moist soils I was talking about, the atmosphere I was talking about. This is the amount stuck inside the leaves of trees, and this is the part flowing in rivers. We're talking about a very small part of the Earth's water, and that's the part we care the most about. And yet these are the parts we have the most limited measurement knowledge about where it is and how much is there. This one, I just want to raise it as a way of saying this is the water cycle. We have evaporation over the oceans. Then so the storm clouds develop over the oceans and they carry that evaporated water out of the oceans. They carry that, the storm clouds carry that through the atmosphere over the lands. And then it rains. You know, it's going to rain later today. We've heard all about that, right? Tonight. And then it rains on the Earth's surface. That's the precipitation coming down out of the clouds. And then that rainwater is going to collect in the rivers. Some will soak in the ground and create what's called groundwater that we drill our wells for. And half of it is going to evaporate and half is going to flow in the, so we can divvy it all up. Half will flow in the rivers, half will evaporate. Of the stuff flowing in rivers, some will soak in the ground and become groundwater. And as it flows through the rivers, it comes back to the ocean and evaporates again. We're not creating new water and we're not getting rid of water on the planet. There's no new water showing up somewhere. We're not using up water. We're not, oh my God, I've used it all up and there's no more water. So it's fun to do this with, you know, fourth grade boys. You tell them, okay, so when you have a drink of water, what happens to that water? Hey, Dad, I pee it out in the toilet. Hey! It goes through your body. You're not, every cup of water you drink doesn't disappear. Otherwise, we'd be ginormous, right? So the water goes through our bodies and we treat it, it goes back. Same thing with the Earth. The water's continuously cycling through the Earth. So we're not using it up, but we are experiencing through global warming less water in one place, more water in another, at certain times as well. And that's our greatest challenge, is how that water is used up that way. That's use of water. Okay, so there's our global water cycle. I don't care about the numbers. And this math down here, I decided not to talk about it. But there is a coupling between that water cycle and global warming, and that's what this slide is about. It's through evaporation. That's the coupling. And so you have the heat coming down. Again, these are just pretty graphics. Don't worry about the math and all the other gibberish here. But the amount of heat that comes down upon the Earth from the sun, that's what we call radiation. So that's just, and you know, if you wear a black shirt, you get warmer. And if you wear a white shirt, you get cooler. These are the kinds of things we all know. And that's what radiation does. Okay, so the Earth soaks up some of that heat, and the Earth radiates back some of that heat. Now, if there wasn't a balance, the amount of energy going in, and we got the amount of energy going out, this energy going out had better equal the amount coming in. And if it doesn't, the Earth is going to get really warm or really cold. And I don't mean like global warming cold. I mean like Mars cold, like moon cold, no atmosphere. That's not what we want. And global warming is only a very tiny fractional shift on this kind of stuff, which I'm not going to talk about. I'm not going to talk about what greenhouse gases are and all that. But what's the coupling? It's this part right here. So this is the heat that you can sense with a thermometer, feel with your body. It's called sensible heat. We scientists are really smart. We label, sometimes we actually use sensible words. Then this one, you're like, what's latent heat flux? Well, that's, we don't use a sensible word there. Latent heat flux is more or less a mathematical term. It's the difference between these two, the amount coming in, the amount we can sense. This is what's left over, and it's actually the amount of heat that's required to evaporate the water. And then when it rains, that heat can be released. So we call it a latent heat. It's a sort of mathematical heat. But this is the heat that's being used in global warming to evaporate and move water around the planet. I'm not asking you to know this as much as just realize that's the coupling to global warming. And it's something you already know. I have a blacktop driveway, and so when my son goes out and washes the car, I pay him $5 to do this. It's very useful. Children respond to money, especially when they can buy Legos with them, right? So if it's a hot summer day, he can watch the water evaporate off the driveway very easily. And if it's one of those cold spring days and I'm an ogre of a dad, I send him out there and it's 45 degrees, wash the car. It doesn't evaporate as fast. And so I like those kinds of analogies. I don't know if they're useful for you and children or not, but that's latent heat flux as a very generalized way of looking at it. And that's the coupling to global warming. We're going to skip this slide. This is one of the ones I shouldn't have put in there, and I did, and it just blah. This slide is a basic version of the one you just saw before. We have the atmosphere. It holds so much water. The size of the box is not how much water it holds. The number is what matters. So the atmosphere holds only 14 units, and the units are buried away down here, but just 14 units. Oceans in comparison are gigantic, 1 million units compared to 14 units of water. Land a little less, and there's a lot trapped in glaciers. The other thing we get concerned about, and this is what's called a water balance. And all we're talking about here is how much water is evaporated from the oceans and goes into the atmosphere versus how much rains back down into the oceans. And what we like to say then is if we look at the atmosphere and we figure out, okay, how much is evaporating off the land as well, if we add that number and that number in terms of the evaporation off the land and the oceans, it should equal the amount of rainfall or snowfall and rainfall over these two. And they do. These numbers are close enough when you add them up. Because if the numbers aren't equal, then the atmosphere could be really getting gigantic or shrinking. Because we'd be filling it up with lots and lots of water being evaporated from the oceans. That's not happening. The atmosphere's not getting any thicker or thinner. So we know this is stable. The oceans are getting bigger. The sea level is rising. We're very accurately measuring that, and so on, so on, so on. So we can measure that. Glaciers, you all know, are shrinking maddeningly fast. So this is not a stagnant number here. Especially this runoff melt from them is getting bigger. But the atmosphere we tend to think is being fairly stationary. So that's your basic overall view of all the ugliness you saw in this slide. So I'm just trying to break it down into the basics here. All right, so this, before I launch into any of my own particular research, all this is to back up and say, so how do we measure these things? How do we go back to this? How do we know the numbers in here? Well, what we need to do to know them in the detail necessary to calculate these water balances so we understand how much is being gained and lost in each important box. And like I say, it's only fractional amounts that we're talking about here of energy that's changing the water cycle. So we have to measure to a better accuracy than what the cartoon like this shows us. So how are we doing that? That's with these types of instruments. Satellites give us a global view of the Earth. And it wasn't until the 60s when we really had these global views. So we have satellites that take pictures of the Earth. Let's see here. Of course, MODIS, Landsat and MODIS. When you go to Google Earth and you look at the pictures on there, a lot of the ones when you're pulled out from the really high level elevation views, you know, you're sort of like, whoa, I'm looking at the whole continent view or maybe a statewide view. That view is coming from this satellite. That's where the data comes from. And Google gets it for free because NASA gives taxpayers, gets it free. And then all these other data sets, these are more research-oriented data sets that tell us about things like sea level, tell us about the mass of water, how much water's on the planet, tells us how much it's raining on the planet. This mission here told us about the elevation of the Earth's surface. And so when you use Google and you look at the elevations, particularly outside the US, they're coming from this mission here. And now when we begin to put all these together, that's how we're going to construct a water cycle. So okay, so I babbled enough. Does this give you a framework, a sort of conceptual idea at least? Am I connecting at all? Okay, this is what happens when I lecture, right? The students all go, yeah, dude, what's on the exam? You know, and I usually stop and say, this is on the exam.
I don't know if this makes any difference, but what about when we just talked about the water, and there's always about this amount of stuff at the end of the year with my class. But I told them, okay, you always have this amount, but we have to worry about is pollution. Does pollution of water come into effect anywhere in this?
Water sort of has two things. A quantity, you can measure how much, and a quality, is it any good? And so you're asking, is it any good? So we pee in the water, right? And you know, you got to send that through a filtration system and we can clean up the water. As it turns out, we do in the US a decent job of cleaning up the water. There are pollution events that tend to be very localized. One of my favorites to show the students, so those of you from Cleveland, remember the burning river, right? The Cuyahoga burning river. It actually caught fire a number of times. And I tell students that, yes, it's our parent, not me, but my parents. I blame that generation. They were so smart, right? Those guys were so smart. You kids don't know nothing. Yes, but the river had to catch on fire at least 3 times before we decided it was a good idea to form the EPA. That burning rivers are bad. It took us several times to figure that out. How smart was that generation, right? Your parents aren't always so smart as a generation goes. We have wised up. And so we do look at pollution. So that's one example. The Cuyahoga River is what indeed triggered the formation of the EPA. Richard Nixon signed the EPA into law. We have Grand Lake St. Mary's, sort of north and westish of here, which is being polluted through algae growth. And how is that happening? Well, fertilizers from farmers who are trying to grow crops as much as they can, because they got to make a nickel off their land, right? And so grow more corn means more fertilizer. Well, that fertilizer, when it rains, washes off the land and into the lake, which really encourages the growth of algae. They love this fertilizer. And they then suck oxygen out of the water, and the fish who used to live there can't breathe anymore. And so that's a pollution. But it's not the pollution of the evil steel mill that's just got this pipe that's forcing sewage or whatever out, right? The pipe is a point source pollution, and what I've just described is sort of a non-point source. That's what they call it in the language, because it's coming off from all kinds of farm fields. Okay, so I don't know if I've answered your question as much as I've sort of talked a little bit about what pollution is here in Ohio. It is a grand challenge to have clean water. NASA doesn't really deal with clean water in a global perspective. So what I'm trying to frame up for you is that how much water we have at any one place in time in connection to global warming is a global question. Pollution often is a very local question.
But the pollution, like whether water is polluted or not, doesn't affect how it's going through the water cycle.
Not really. Because pollution is so localized, I mean, I'm now off the cuff here. I don't study this, but this is my gut instinct. Grand Lake St. Mary's is so small, but it's so very polluted, but its contribution to the water cycle is very small. On the other hand, locally, it's very important. But on a global scale, not so much. So is there enough pollution? We're saying, well, how would pollution stop evaporation or increase evaporation, as a for example? Okay, let's change the color of water. We can change the color of water. If we make water more dark, it gets hotter, right? We all know that. I'm wearing a dark shirt, I'm going to be hot when I go out. So if water's darker because of pollution, okay, it'll get hotter then. It might evaporate more. I'm making this up on the fly. Okay, that could be a consequence of pollution. I don't know that it would be that important in the compared to global warming. That doesn't negate the importance of pollution. Pollution is fundamentally just a key issue. Here in Ohio, we're really blessed. We live in a state that is awash in water. Nobody here ever talks about, oh, I ran out of water. In fact, I find it weird that the Delaware Water Authority tells me I can't irrigate my lawn on a few days a week. I get that. I know why they're doing it. It makes sense. But we got too much water. We don't know what to do with it. And if it's polluted, you know, one of the things we always say is the solution to pollution is dilution, right? Just keep diluting, you add more water, in other words. But we're not so, you know, you go outside of Ohio, it's not so well, right? There was a big, huge drought. I should have put a drought slide in here, but the Midwest, particularly going out to Iowa, was in an enormous drought all last year. So we don't understand in Ohio the importance of water because we have so much of it. All you have to do is move to Phoenix, and wow, you know, huge difference. Atlanta, huge difference. Tennessee, even, oddly enough, can experience drought. So we don't have to go very far to experience drought. So I babbled on about it. I hope I came close. Anybody else? You racking your brains for questions? Okay. Well, let's, cut me off, by the way, whenever I'm supposed to be done. Just, you know, like the old cartoons, right? Did everybody watch the Bugs Bunny cartoons, right? I love those, right? And they got the guy with the hook, and he, right? All right, so hook me. All right, so what I want to talk about now is my own personal research, and one piece of it is in the Amazon. So my philosophy was, well, until we have these great satellites that are supposed to be launched over the next several years, that'll give us global views, we have satellites that give us conceptual ideas and allow us to make some basic measurements to get these ideas framed up in terms of what we know right now. All right, so there's one called GRACE. You see the acronym. And so I decided I would study the world's biggest river. The Amazon is the biggest river in the world. It's 10 times the size of the Mississippi. It's just massive on any scale you can possibly think of. We'll put it this way, the Ohio River would really border on whether it would even have a name in the Amazon. It's that small. Crazy, right? So one way to study that is to use the mass of the river. It's so big, the mass of the water actually will compress the Earth's crust by about, let me convert 10 centimeters, to about 2.5 inches to 3 inches. So this big annual huge flood wave, you've all seen Jeremy Wade and River Monsters and all that, right? And the crazy guy who goes, I mean, that guy's amazing, right? So the big flood wave comes through the Amazon once a year. Every June, the city of Manaus is flooded, and the earth there will compress. So I won't do, like, it's more like it'll compress literally by as much as I'm moving my fingers. So, you know, jump on the earth. You can't compress this earth. Well, you can't do it. So imagine how much mass it takes to compress the earth's surface. Then when the water goes away, it bounces back. It's an enormous volume of water. So it's so large that we can actually measure that mass from space. This is an amazing concept here. So here's a satellite. It's about the size of this desk. There's its twin over there, size of the desk, connected by the ARTIST ray beam. And what that ray beam is measuring is the distance between those satellites to 1/10 the width of a human hair. My hair is a little thinner than some of yours, and so maybe, you know, but anyways, very, very accurately. And what happens when this first satellite approaches a big mass like the Andes Mountains is that the mass of the Andes pulls on the satellite. It's like, why is the moon next to the Earth, right? Because the mass of the Earth holds the moon there. Why do we orbit around the sun? The mass of the sun holds us close to the sun. I won't go into orbital dynamics, but that's the way it works. Same thing here. The mass of the mountains will accelerate that satellite, make it go just a little faster relative to this satellite. And we measure the distance between them, and we can turn that distance into acceleration because it'll speed up and move a little way away from this one. And then when it goes past the mountains, it'll slow back down, and then this one will speed up. So instead of mountains, imagine the mass of the water as the way it speeds up and slows down. But because the mountains are stationary in time, they just sit there, they're there all the time, this gravity signal, this mass signal is stagnant, doesn't change. But the water moving through the Amazon is different all the time, it's changing. And these satellites can measure that. So this is what we call a mass measuring device. So I love showing this slide. I like to tell students that, you know, Hollywood and pop culture know all about the Amazon. What about you scientists? You're so smart. So this is Gary Larson, right? I mean, he's like every scientist's dream guy, right? So here he's telling little Jimmy, you can buy a bicycle if you can tell me how much it rains in the Amazon. I mean, what a quirky thing to tell anyone, right? I mean, other than me, I think it's funny. I can actually answer the question. I get the bicycle. Well, Jimmy doesn't know, so away we go. Over here, we've got Survivor, Amazon from years ago. And then we got J-Lo and Ice Cube, Did you see the snake eye? Did you see it up there, the snake eye? Gives me the creeps. This is our Hollywood view of the Amazon with this boat here or these trees. I mean, and that's the way it does look. I've actually been there once. I'm a satellite guy. I don't like to get dirty in the field. It's very frightening to me. You know, hopefully you'll hear from field people. They're very courageous, and I like Google Earth, man. Like espresso, Google Earth, espresso, Google. So anyway, that's the way it looks. So another reason why do we care, particularly about the Amazon and about water? Well, as it turns, here's something we all like to say. We all say the Amazon and the Congo, these big giant jungles, are going to save us from our carbon sins. Keep pumping away. I'm going to go drive my SUV home. Oh, God, I hate myself. I do drive one. I keep telling my neighbors I'm going to get me one of them electric cars. I love electric car, right? That'd be so cool. I'd be the coolest dude ever. We'll come to that someday. Anyway, so we got our carbon sins. We're pumping carbon into the atmosphere because we burn carbon monoxide from the carbon fuels. And so then we say, but those trees in the Amazon and Congo, they suck the carbon back out of the atmosphere. They're going to save us. Some people have called them the lungs of the planet. You're like, great, plant more trees. Thank you, Amazon. And you guys down there cutting the trees down, stop that, shame on you. Go figure out how else to make a living. We get very provincial in our thinking. We get to telling others how to live when we ourselves aren't willing to live the right way. So I'm very cautious about this notion about deforestation and what does that mean. It's a much more complicated problem than simply stop cutting down trees. In any event, here's another very interesting article. It's a really amazing thing that is now published 10 years ago. Really amazing stuff. What they showed us in this paper, so what are you looking at? You're looking at a map view of the Amazon, and I know you're kind of pulled back a little bit, but the Atlantic Ocean is way over here. Let me see if I've actually got a map that'll show you. You can kind of see it here. So the Atlantic Ocean is over here, and South America comes down around like this, and the mountains, the Andes Mountains are over here, and Venezuela and Colombia and so on are up there. And so we're looking at this map view, and everywhere it's purple is water, and everywhere it's black is land. Now look, this is where the two rivers meet together at the city of Manaus. 1 million people live right here, 1.5 million, and then nothing elsewhere. And 6 million square kilometers, nothing, except for a couple other little tiny towns. But 1.5 million live right here. It's a big commercial port. Ships, ocean-going boats come all the way up to here, and they dock right over here. So these two rivers come together. This is the Negro River, which is Portuguese for black. And you can see it's black. Brazilians are kind of smart, right? They name things the right name. This is the Solimões or Amazon River. It's loaded with sediments, brown. They're coming off from the Amazon. They're eroding away. These two rivers meet right here. It's called the meeting of the waters. And you can get in a boat and do what I did, and you can put your boat on right on the other side of that and stick your hand in the water, and you're like, whoa, it's brown, it's black. Why is it black? Anybody have any idea why it's black? Anybody ever played in a pond and went, ugh? You know, you look at the organic gook all around your feet. Exactly. It's loaded with carbon, loaded with dead trees and dead leaves and dead stuff that is decaying, and it's blackening the water. You can see the carbon with your own eyes. But guess what? The amount of carbon that's bubbling up out of the water through methane, in particular in this study, through CO2, carbon dioxide, as that decays, carbon dioxide is given off, and it just bubbles up out of this water surface straight into the atmosphere. That amount of carbon that's going back into the atmosphere, just like we put carbon in the atmosphere through burning our cars, our fuel, so carbon going back into the atmosphere is 13 times larger than what you can see with the naked eye. That's an amazing amount of carbon. And it's so much carbon that the amount that the trees pull in is about the same that the water gives back to the atmosphere. So the water plays a crucial role. The surface area of the water, how much water there, how deep the water is, controls the bubbling up rate. This amount of carbon that goes out of the water into the atmosphere is about the same that the trees pull out of the atmosphere, and therefore the Amazon is not going to save us. You get my point, right?
Right.
So, yeah. We don't know about the Congo. Congo is a very different story. The Congo water flows are very different from the Amazon. I won't go into all the details, but so what I'm trying to do is connect in your mind the notion that maybe it comes back to pollution, right? This is in a sense pollution, in a sense. So it's not just we want to measure how much water we've got around the world. We're also very well aware that there are other very important aspects of water that connect into that, and particularly into influencing global warming. Okay, so what do I really want to say about this? I don't know. I mean, when do I get cut off here? Okay. I don't really, I mean, okay, so this is what GRACE measures. It's very coarse. It produces a big giant blob and tells you it's raining a lot here where it's red. You see the outline of North America. There's the Amazon River. This is April, the first 2 weeks of April, second 2 weeks of April, first 2 weeks of May, second 2 weeks of May, and then you go all the way across and get a whole calendar, and it tells you it's raining a lot here and not so much at this time. I'm not really concerned that you understand all that, the scaling. I don't want to go into all these details. I think this is just too much compared to what I intended to talk about. This is what I do want to do. I want to show you this. This is far more important to do this. Let's make a connection between what I just told you about the Amazon, just in a very brief introduction, and the Congo. We can make a comparison between the two. So here's some image I stole off the internet because, again, I don't go to the field. I just internet. There's a lot you can do on the internet. I'd be lost without the internet. So my friend Lael, she took this picture of the Amazon. You're like, hey, they look the same, right? I mean, they're big, wet places. They're green, leaves everywhere. It's the same. Guess what? They're not. One of the things we found, this is where I really want to do a little compare-contrast, and this is a more straightforward slide to understand. That's why I want to spend some time on this one. So we've got time across the x-axis, and you see the years going across here, increasing in time to the right. Same thing here. And we've got the elevation of the water here, higher, versus lower water level. And the red line in both cases represents the river, the nearest river. In this case is the big Amazon River. I forget, I think this is one of the major tributaries call it the Congo River. And you see that over time the Amazon River goes up and down, and each and every year it goes up and down. And that's that big flood wave I was talking about. We can also measure the water levels on the floodplain right next to the river. And they're also in blue going up and down. And one of the things we teach students is that the coupling between the water on the floodplain and the water on the channel is like a bathtub. So you can picture yourself here where I'm the river going down the middle, and you guys are the floodplain out there, and the water levels go up here and shoot out over the floodplain, and they go up and down together exactly the same. We call that the bathtub model. And that's the Amazon in this particular example. As in everything, it's more complicated than that, but for our purposes, that's the example. So you'd say, okay, the Congo is a big green wet leafy place just like the Amazon. Shouldn't it behave the same way and therefore have the same carbon dynamics, the same hydrologic information and so on? No. From a satellite, here's the water level going up and down on the Congo River. It's a little more jagged. It has 2 bumps per year as opposed to 1 bump or 1 major bump per year. But it is going up and down. But look at this. This is the floodplain right next to the river. It doesn't do anything like this amount of up and down. It's very subtle, hardly any up and down. Look what's worse. The water here is always lower in elevation. The red line is always less than the blue line. It's always below. So there's absolutely no, water does not flow uphill. I have to dispel students. No, they're smart enough. They know that. They get that, right? Water doesn't flow uphill. So there's no way the water in the Congo River flows into its floodplain, into the wetlands around it. It's a major difference in the way carbon would be produced. Carbon is out on the floodplain. It's being evaded it's being bubbled up out of the water surfaces, out on the floodplain. But if that floodplain is not being flushed by the water of the main river, what happens to that water out in the Congo? We don't know. We don't know what happens to that water out there. It's just sitting there. Is it stagnant? It's not moving much. What's happening to it? How does it fill? How does it empty? Good questions. But it's not at all, in terms of its hydrology, like the Amazon. And so here's this other big green wet leafy place that's supposed to save us from our carbon sins, and already I can tell you it is got to be different than the Amazon, just based on the hydrology alone. So these are two comparisons which I find utterly fascinating, and we spent decades of time on this one. Many, many, many research teams around the world are studying the Amazon. The number of people studying the Congo is orders of magnitude fewer. I could probably count on two hands. Yeah, I could count on two hands, maybe even one hand. I'm not exaggerating. 1 to 2 hands, the number of teams in the entire world studying the hydrology of the Congo, whereas it's 100 to 200 teams studying the Amazon. Yeah, why? Yeah, great question. Well, it's a dangerous place. And there's scaredy cats like myself who don't want to go there. It's a frightening place, in all seriousness, it is. It's not a safe environment. The Amazon's very safe. You can go there and you can go anywhere in there, anywhere within Brazil, and it's a safe environment. You can collect water samples, you can spend a lot of time there. There's infrastructure to help you out. There's just all kinds of opportunity. The Congo, wow. Completely politically unstable. I mean, just Google Congo, Democratic Republic of Congo, and so on. These are great challenges in terms of the economic infrastructure of the countries that are in the Congo Basin, their political structure, poverty. These are very unstable locations, and so it's very difficult to get people to go there and do things. We're only just now, as scientists, making a connection to the local people who live there and are working in their various schools and universities. We're only just now making those connections. So that's the major difference. All right, so I've talked a lot enough. I hope I've given you some excitement. I'm not going to talk about that. There's some, yeah.
When you were talking about the Black River, why is it so black? Why is there so much more
Yeah.
in there than other rivers or
Yeah.
places, water sources in the world?
It's a great question. So I don't have a good pullback view of the whole Amazon basin. But what happens is so hopefully you can see that this is the Atlantic Ocean way over there. And the Andes Mountains I don't have drawn in here, but they're over here. So the brown river in that map is this one. That's called the Solimois River. And it's draining off from all of this highland, high mountains. The Andes are gigantic. They're bigger than the Rockies. And so they're eroding those mountain chains and carrying that eroded sediment, turning that river brown all the way through here. This river, the Negro River, that's it. It doesn't really drain any high topography. This is still pretty low topography. It's like draining Ohio. But unlike Ohio, this is loaded with vegetation. I mean, just trees everywhere. So very little sediment, but tons of organic material is coming from these trees that decay and die and their leaves fall into the river and so on. So that's the fundamental difference, is the drainage area is largely organic, or let's say less sediment here than here.
Is it making the Amazon black? Are they going to mix?
Oh yeah, if you go downstream, so that picture view I was showing you is standing here looking upstream, but if we go downstream about 20 kilometers, 12 miles, if you go downstream of here about 12 miles, this is now pretty well mixed. And because the volume of this river is about 3 times the size of that river, together they mix and become mostly brown going down through there.
So eventually over time it's going to get worse.
Well, the organic just keeps getting dumped into the ocean and so it's not like it's getting more and more organic. It's the same amount of trees living and then dying each season, and then the river flushes it out. So it's more of a cycle than it is, we're getting more organic. It's just the same, plus minus, over time. And the Andes the sediments here are the same, more or less, over time.
But the trees in the Amazon is just enough to keep it balanced, so it's not going to help us as far as the other carbon that we're putting into the earth with our vehicles and what.
Well, actually, there's fewer and fewer trees. The deforestation is an important issue. I don't mean to diminish that, but it is an important issue. And the reason why people are cutting down trees is because they make money from that, right? So, and more trees have been deforested, and there are lots of studies suggesting that over several decades, plural, that the entire forest will be gone. So it's worth being aware of that, but how fast it's happening, where it's happening, and so on, and why it's happening. These are much bigger sociological questions. And so we do believe trees are definitely decreasing in number, no doubt. In the back, I'll go to the back.
We were just talking about, did you ever seen a picture of the delta going into the Atlantic from
Mm-hmm.
the
Mm-hmm.
Amazon? Because I've seen the Mississippi and the Nile, I've seen quite a few of those, but I've never.
So the difference between them is there's one fundamental difference. There's a big offshore current here. And so all the sediment that comes off the Amazon River gets carried away from here. In the Mississippi, there's really not much of a current through the Gulf. Exactly. So the sediment just gets plopped out there, and it lays out there very politely, and actually becomes a great source of oil because there's organics. Just in the Mississippi, there's organic as well. Give it a million years, converts to oil. So somebody, is that, okay, cool, good. All right, so who's next? All right, go with you.
I noticed that your rapids and the flooding seem to have remained pretty constant, yet several of the countries are starting to experience really different patterns in their rainy seasons. Either they're getting more rain or it's coming at a different time in the year that they were expecting. Why is it that the flood pattern seems to have remained pretty constant, yet rainy seasons seem to be
Okay.
unstable?
Great question. I don't have a good answer for you. It is an active area of study. In the Congo in particular, we have a real paucity of measurements. We have papers that we have published in my team and my colleagues that show that the satellite measurements of precipitation don't actually match up with the water flow measurements from satellite, that there's a difference between these. And so already the measurement could have some errors attached to it, which means the next satellite gets launched needs to be improved, and they have improved it. Where we do have adequate measurements, more so in the Amazon, there are droughts. So you can see, for example, and I know a drought in the Amazon, it's always wet, okay? It's just drought means less rain. So here you can see that in 2005, it's kind of a little less than what we have in the range here. Some of the rainfall patterns and whether it rains a lot or not so much is connected to things like El Nino. And so we experience El Nino here in Ohio every plus minus 7 years. It could snow a lot more, rain a lot more, a lot less. Temperatures can change. The same thing can happen in the Amazon. El Nino and other types of global cyclical phenomenon and climate can impact the amount of rainfall. One of our bigger challenges is when we look at those types of, we call them oscillations, El Nino, Pacific Decadal Oscillation, the North Atlantic, blah, 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 blah. All right, so frame of reference. A couple of winters ago, remember how warm it was? Like we were like, dude, it's March and 80 degrees. This is awesome, right? Global warming, bring it on. Well, it was that way because the North Atlantic Ocean was warmer than usual, and it kept the Gulf Stream to the north. Okay, that's an oscillation that happens in the ocean temperatures. Why do we in Ohio care about ocean temperatures? There's your example. These oscillations that happen in temperature phenomenon you have them doing this kind of thing over time, and then the global warming signal is more of a stationary or a linear thing. How do we tease those apart? It's really complicated when it comes to water. Temperature, it's easier. We can measure global temperatures very well, very accurately, but the impact of those on water is a whole other story. So I haven't answered your question as much as I've tried to give you a frame of reference. Any more questions? We good?
Thank you very much.
All right, all right. Thank you. Thanks for having me. I appreciate it. Need me to